Okay, let's do a recap. Let's do a recap of what we went through yesterday. And welcome back, Shannon. After 3 days, you missed.
Yeah, it was fun.
So, okay, not something that you want every day, I guess. So, the last lesson I went through the f equals to dt, and I explained to you the difference between this and this. Can anyone tell me what's the difference between the two? The one on the left is average force. Yes, correct. The one on the right is at a point of time. Yes, correct. That's the same idea that we have for average velocity and instantaneous velocity. Yeah, so we'll just recap over that. And then I went through with you the last thing that I went through before I left the class was the integral f dt is equal to delta p. Now, this is basically the area under an ft graph. Remember? Yeah. Tricks that I can play, I'll just be mindful about that. Tricks that I can play is that I give you this in kilonewton, I give you this in milliseconds, so just open your eyes wide. Look out for all these tricks in the question, which I'm going to give you very soon. Okay, as example. There's another name given to it, I'm not sure whether I have given you that name for this thing, it's called impulse. Yeah. Impulse, which is the name for this thing called change in momentum. Why not just call it change in momentum? I guess probably we'll just call it impulse is faster. Yeah, so the name given to change in momentum is called impulse. Impulse is the change in momentum. So I'm going to give you a question. Alright, I'm going to give you a question building on what we learned last lesson. And this force is exerted on an object moving at 20 meters per second in this direction. Your task is first to find the change in momentum of the object and find the final velocity.
It's to the right, 20 meters.
20 meters per second towards the right. You have to use this idea. You look on your face and then it's like total. Are you alright? So all you need to know is that the area under this graph is the change in momentum, and momentum is mass times velocity. If you have any doubts, you can ask Yanita. I'm sure that she's willing to help you, and if she cannot help you, come to me. Okay? Guys, go back. Got a feel of how to start. In your mind, there must be a map appearing to you like find this, therefore find this, therefore find this.
Before the exert on the changes.
Again?
Before the exert. Increase and decrease. Like the graph.
Yeah, increase and decrease. Of course, the last part is what students don't really like, but you have to know, draw the momentum against time graph. Using the idea that f is equals to dp dt. Okay, hang on. Yes, correct. I see the defense goes. Careful of the milliseconds, and I'm making it explicit to you. Be careful of the milliseconds. Be careful of the time set for formula.
Because we're using the graphical method now to calculate change.
Yes.
So it's like 4 times 10 to the power of 4.
Yes.
Multiplied by 10 divided by 2.
Then times 10 to the power minus 3, huh?
Yeah. Then divided by 2.
Yes, correct.
But then when you
Zero
use the
triangle.
f equals to change in momentum over change in time, it's 4 times 10 to the power of 4 multiplied by change in time.
4 times 10 to the power of 4 divided by change in time.
Multiplied by
No. When you do f times dt equals to dp, right? Or the other way, delta P equals to F times delta T. It's only for a small amount of time. So it's only for that small period of time, that small delta T over here times F over here is that small change in momentum. Yeah. So if you use that method, if you take 4, then you'll be finding this change in momentum, which is not right.
So you always have to draw.
Your F is changing actually.
So you always have to draw the graph.
Always have to, but this graph is given to you. It's part of the question. Yeah.
But if
it's
F is
part of it.
constant, then you just write.
If F is constant, exactly, which is the easiest form, then your method will work out, just F times 2. But of course, come on, IB is your class. Can I show you how to do it? I'm sure you know what's the area of triangle, right? Because it will surprise me. Yeah, this will surprise me. Suddenly pi r square comes out. Oh, that would be really shocking really. So half of delta P is equals to half times 4 times 10 to the power 4 times 10 times 10 to the power minus 3. Actually, at this point of time, you shouldn't need calculator before. You really shouldn't need calculator. Come on, don't think so yourself. Yeah, so this one will be 5, this one will be 2, and then this one will be 2, so it's 200 kg meter per second. Yeah? Really don't need calculator. Now, so delta momentum equals to 200 meters per second, therefore final velocity equals to 200 divided by 10 equals to 20, right? You just take momentum divided by mass, you get the velocity. Right or not? What's wrong? Excellent, yes, right, this is the change. So this is wrong because the student, me, didn't realize that actually change in momentum is equal to final minus initial, which is equal to 200. Now what is the initial momentum? 2 times 10, 20 times 10, so it's 400 final. This is 200 over here, shift over becomes 400. And therefore final velocity, which is equal to this divided by the mass, will be 40 meters per second. Any issues? Notes? I can tell you a few areas that students will make mistakes. This is one area that will make mistake, this is one area that will make mistake. The other part that will make mistake is exactly what I told you just now. That they didn't realize that it is change momentum. Took change in momentum as momentum. Okay? But people, this is actually a discipline of the mind. Whenever you look at things, you in your mind describe it carefully. Force, net force. It's kind of tagging, describing. You need to be very clear. Okay? If you have done part 2, which I've already done with you, can you try part 3? How will the momentum against time graph look like? Now, for those of you who can do it in the breeze, think about what if I were to exert the force in the opposite direction. Same situation, just that the force in the opposite direction. Think about it. To do this, you need to realize that F is dp dt. So if you look at F equals to dp dt, graphically, if I were to draw a momentum against time graph, how do you get F on the graph? Next time. So if you describe the gradient now, the gradient should increase from 0 to a maximum gradient to a minimum gradient. Yeah? So therefore, if you have a momentum against time graph, it increases to a maximum gradient and then decreases to a minimum gradient. Correct. Wait. Correct. Start like vegetable already.
So it's still already moving at 20 meters per second, so doesn't it have some initial momentum?
Okay, yeah, right. Excellent. So what happened is this is wrong on 2 counts. First, it should start from here. So it should start from here. And then what else? You see? It should be like this.
Yeah.
Now the problem that some students will have is that you see, when the force decreases, somehow the optical illusion over here is that since the force decreases, the momentum must also decrease. that we can make. So when certain things like, say for example, when acceleration decreases, is the object slowing down or speeding up? Still speeding up, exactly, but speeding up at a decreasing rate. So be very sensitive to this kind of cognitive traps. Yeah.
So is this the case where force is in the other direction?
No, this is still
No,
force in the same
oh,
direction.
okay.
It's still force in this direction. Everything is still this
Yeah,
direction. After we've done this, then what happens to this whole process if the force is in the reverse direction?
Then that will be increasing and decreasing rate.
Increasing and decreasing rate. What do you mean?
Isn't
The momentum.
the graphic like this?
So this is for the force in the towards the right or towards the left?
Force to the right.
To the right, yes, correct. So how would the graph look like if the force is towards the left?
A bit down.
It'll be going down, right?
Yes, correct. It has to be this, right? And if you remember the calculation, actually the change in momentum will be exactly 200, so the object will eventually come to rest. Now this graph that I'm going to draw, in case it causes confusion, this graph I'm going to draw is for the case where the force is resisting the same force, but now the force is towards here. Okay? So if you still remember, the change in momentum is actually 200, so 200 in this direction now. So what's the final momentum of the object? Initially you have plus 200 kg
So
per
it was
second.
negative.
What's the final momentum?
It'll be
So it will be like this.
Yeah, because the change
So
in
it's just
The
down.
change is now negative. Yes. So if you write the equations properly, it will be Pf minus Pi equals to negative 200. So what am I trying to do over here? I'm just trying to sensitize, make it more sensitive towards direction. Remember, momentum, force, vector, 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 vector. Yeah? Always vector. Add, subtract, whatever vector. Remember this. Yes. In this case, it goes down to 0 because the initial momentum is 200, just nice, and the change in momentum happens to be 200. It's a special case. Yeah? It's a special case. Cool. So this is an example of how an exam question can be asked. And this is one of the most popular questions I think. But if I give you some weird graph, I can give you a trapezium, whatever, whatever shape. Of course, if I want to make your life more difficult, then I can give you something that will require you to integrate, say, this is kt squared. Yeah? It doesn't matter, it's just integral. Come back. Once I'm done with the normal, I'll come back and show you how to do it. Same concept, just that you apply calculus. I can give you different shape, but the concept is the same. Area under the graph is changing momentum. Cool. Quick scan. Anyone got any issues? Just a quick 10 seconds. Still okay, still alive. Okay. Okay. Now, let's take a look at two objects colliding. When A moves towards the right, B moves towards the left. Okay? I'm going to derive a very important conservation law, which you're going to realize it yourself. Now, do you agree that F exerts A exerts a force on B this way, and B exerts a force on A this way? Newton's third law. Now, what Newton's third law says is that FAB must be equals to negative of FBA. Equal and opposite.
Yeah.
So cool up. Now, what I'm going to do now is that I'm going to multiply by the time of the collision on both sides. Nothing has changed. The equal sign is still there. I multiply both sides by the time of the collision. I'm going to make an assumption that the force is constant. That's a stupid assumption, but it is. Let's assume it's constant in simplistic case. So therefore, do you agree that F times dt, what did you learn just now? F times dt is actually delta B. Exactly. So this is change in momentum. This is force by A on B. So this is the change in momentum of B. Now, the same thing happens on the other side, just that this is change in momentum of A. Bring it over, and you see that change in momentum of B plus the change in momentum of A is equal to? Excellent. Now this means that the total change in momentum is equal to 0. which means that the momentum of a system that has no net force acting on it, other than those two forces, the momentum must be conserved. It's conservation momentum.
Oh.
So as long as there's no resultant force.
Exactly. As long as the two forces are internal, that means A on B, B on A, there's no resultant force like frictional force or air resistance, momentum will always be conserved. Now, as you write this down, I'd like you to think carefully. Then why is it that if I were to drop a pen over here, the momentum of the pen increases? From no momentum, got momentum. So by that, the conservation momentum. Yeah, yes, exactly. So you see, no momentum, right? Got momentum.
But there's a resultant force on it, right? Because when you're holding it in place, you are exerting an outward force. So when you let it go, there is a resultant downward.
Excellent. There are two ways of seeing this scenario. When you let go, there is a resultant force called weight acting on it. So it doesn't hold. Yeah? But there's another way of seeing it. If you consider this pen and the earth as one system, when the pen falls towards the earth,
Falls down to that.
excellent. Yeah. Just that you don't see this because the mass is too big over here, the mass is too small. But like what I said, if Thanos, he will pull a planet towards the other planet, then yes, the both planets will come together. Yeah? You watch Infinity War?
Of course.
Last time, yeah. the part where he was trying to kill who?
Lisa.
He pulled the whole planet towards the.
Right now they can breathe on the icon.
The director said he can, things can. Director said he can. Okay, so conservation momentum, yeah? Now let's apply this situation to a very simple one, just to let you have a taste of how it applies. Yeah? You got 4 kg object over here moving at 4 meters per second, and a 2 kg object moving at 2 meters per second. 3. So after collision, this moves at 0.5 meters per second and find the velocity of Now to help you a little bit, to structure your thinking a little bit further, I'd like you to think of it this way. 4 kg, 2 kg, momentum initial, momentum final. Total meaning the combine of the 4 units. So the initial momentum of 4 kg mass, remembering the momentum is mass times velocity, it's 4 times 4, which is 16, yeah? How about the momentum of 2 kg mass? 6, right? 6, huh? 3 and 2, so it's 6. Yes, correct. From all, negative, I know it's lame tricks, but it works. On the teacher side, somehow it works. Every year it works. You know, we tell students, be careful, still works. So total momentum will be, come on, 16, 10, yes, correct. Final momentum of 4 will be, yes, correct. And this is just 2v, right? Yeah, so the total momentum over here is 2v plus 2, right? Yeah, fair enough. So therefore, the final velocity will be, you just need to equate these two. So it's just 4. Okay. And please, next time you check your answer, if your answer over here is less than 0.5, they will be that something is wrong here. And see, it's something must be wrong. Or if the velocity of this object is negative, this object pass through each other, which is impossible. Yeah, so you need to check whether your answer makes sense or not. Yeah. So this is a very typical kind of question. Now what I'm going to ask you to do is, can you find for me the KE total initial and KE total final? Thank you. Energy. Yep. Kinetic energy. Kinetic energy total initial. Even though I haven't gone through the topic of kinetic energy here, but I assume that you know that it's half mv squared. Of course, the question I'm going to ask you to think about is, why is KE half mv squared? Why is it half mv squared? Why not mv squared? Why not 1/3 mv squared? So go ahead and calculate, and you're going to find that What do you think? Will the two values be the same or different?
Should be the same.
Very good.
Go ahead.
It's a rather nice number, right? Half times 4 times 4 is half times 4 times 16. That's 64 divided by 32. 32 plus half times 2 times that's 9 equals to 41 joules. Before. Final half times 4, 2 times 0.5, that's 0.5 plus
Plus 16.
16.5. Right on. 16.5 and 41. Right? And, yeah. So therefore, the energy is lost.
Yeah.
Yeah. In fact, this is true for most collisions. The only case where Ke is not lost is only subatomic particles go. Because any collisions that you have in real life, there will be. Yeah. You have sound, you have heat, you have all these things coming into play. Yeah. So only in like subatomic particle collision where they don't actually collide. There's a positive charge, negative charge. That's when you don't have any contact. And actually, to even talk about sound in subatomic particle world is actually very interesting. Like, what exactly sound? A proton strikes a proton, or what? It doesn't make sense, right? The idea of sound in the subatomic particle world is a very interesting idea. So, most of the collision in real life is where the energy Ke is lost. So, this kind of collision where Ke is not conserved is where we all call inelastic collision. So make a guess. For elastic collision, what's the diff?
K is conserved.
Excellent.
Yes.
Whoa! Whoa. Now for both collisions, momentum is conserved. Now be very careful about tricks in the exams, yeah? That total energy, is it conserved or not?
Yes.
Is total energy conserved or not?
Yes.
Yes, of course. If it is not conserved, Einstein will jump out of the screen. It's Ke that is not conserved, huh? Ke that is not conserved. It's not total energy not conserved. Be very careful about this kind of tricks, yeah? Otherwise, in exams, stress out, see energy already not conserved. Now, in the remaining 7 minutes, I'm going to bomb you with a whole series of equations that will show you a very unique rule that elastic collisions have to follow. Very, very unique. Let's consider two balls over here collides with each other. This is UA, this is UB, and then after the collision, let's assume that they are VA and VB. Any questions?
Collide.
Yeah, just that UA is higher than UB. So some students, well, how do you know that VA and VB must be the same direction? It's okay. You just assume that they're in this direction. So if they're actually in actual real life, if A reverses the direction, you get negative answer. So it doesn't matter. Yeah. So we assume that both of them will go here. If it is not, your answer will be the negative answer. Cool. So conservation of momentum tells us that this plus this must be equals to this plus this. Any strong objections? No, we call this equation 1. Equation 2, if it is elastic collision, can you agree that half ma ua squared plus half mb ub squared must be equal to half ma va squared plus half mb vb squared? Okay, elastic. Energy is K. So for this one, strike, simplify. Now I'm going to do some manipulation. UA squared minus VA squared is equals to MB VB squared minus UB squared. Okay? Still remember your x squared minus y squared equals to? Math, come on. X squared minus y squared is equals to? Exactly. So MA times UA minus VA, UA plus VA equals to MB. You understand why are we doing all these things very soon? Now this is equation 2. Now let's bring down equation 1 in the form. What I do over here is that I'll just bring the A together and the B together. Now when I divide these two over here, can you see that this cancels out with this cancels out with this cancels out with this cancels out with this, leaving me with UA plus VA equals to VB plus UB. And if I rearrange the equation, then you see that it will become UA minus V, UA minus UB, yep, equals to VB minus VA. This equation is only satisfied, two things are very interesting thing. It's only satisfied by elastic collision. And can you see something very interesting about this? It is independent of mass. Which means that I can have a 1 kg mass with a 1000 kg mass. This equation is independent of mass. Yeah? So all you need to remember is very simple one. You take A minus B for initial, you just take B minus A for y. Very simple. Just switch around.
So are there really any elastic collision?
Subatomic particle. Yes. Yeah. That's why we're talking about subatomic particle. In fact, every moment there are billions of air molecules colliding elastically just around you. Now, concern number 1. Do I have to know how to derive this? Big fat no. Big fat no. But I don't know about reform. For me, it's always a challenge and a thrill to be able to derive things. Yeah. So because it challenges your understanding of fundamental ideas. So big fat yes to yes, you have to know this. No to deriving this. But it's nothing complicated. Okay, hang on. It's nothing that you have not learned. Yeah. Question?
So if example right, this derived equation right, if it was disproved right, the whole thing is disproved right.
Cannot be disproved because if you have to disprove that, it's either I made a mistake in my derivation, or it is this is not true or this is not true.
Yeah.
This is definitely true. This is definitely true because of the assumption we make. There is an elastic collision. This is definitely true because it's based on Newton's second law and third law. So unless Newton's second law and third law are wrong, incomplete, yeah, then you will have a wrong conclusion. Which up till now, everyone is still quite happy with it. Yeah, everyone is still quite happy with it. So why is this equation important? Let me give you a scenario, then you'll see why is this formula very useful. Same scenario as just now, 4 kg, 4 meters per second, 2 kg, meters per second, 3 meters per second, 2 kg, 4 kg, 0.5 meters per second. If it is elastic, how will you do this question now? This is B. So let's say we call this, I'm very cautious, you look at how I solve the thing. I'm very cautious about this. I will write V4 minus V2 is equals to U2 minus U4. Why do you think I do U4, U2, V4, V2 rather than VA, VB, UA, UB? What do you think? See, let me just write side by side. VA minus VB equals to UB minus UA, which is the form that I wrote just now. Why write it this form rather than this form? Can you see that if you write it in this form, you have to start thinking which one is A, which one is B?
Yeah.
This one, obviously, I think it's damn obvious. It's done obvious now, right? So there are certain ways that you can go about to reduce careless mistake in exams and use them. Their subscripts are really useful. So V4 minus V2 is 0.5 minus what you don't know equals to U2, which is this one. Let's take this as positive, so it's minus 3 minus 4, which is minus 7. So point V will be equals to 6.5 meters per second. That's it. Very neat. Yeah. As compared to just now, we're going to use mass times velocity and stuff.
So isn't it 7.5?
Okay?
Isn't it 7.5?
It hasn't always been.
7 point. Isn't it 7
It is 7.5. Oh yes. Look at 7.5. Yes. Thanks for it. Okay. So can you see the ease or not? Once I tell you it's elastic, you can use the formula straight away. You can bypass the conservations. Cool. Right, with this I have to end it here today, and I will give more examples. The only part that we have not done in this whole chapter 2 is work energy power, which is what you have done before, so I'm not that worried. Once I'm done with work energy power, then I'll come back to these two topics to show you how integral can be integrated. I will give you examples of air resistance and also give you examples of how rocket works. Yeah, how rocket works. Cool? Okay, I'll stop right